Right, here's video number 2 on the motor effect. Now, video number 1, which you've just seen, shows how we use Fleming's left-hand rule to predict the direction of the force on a current-carrying wire in a magnetic field. Now, what I'm going to show you now, what I'm going to try and demonstrate is how we can accurately measure the magnitude of that force on the wire in the magnetic field. Now, as you've seen from the explanation from the PowerPoint, there's an equation. There's an equation to help us predict the magnitude of this force, and it's the famous F equals BIL equation. Anyway, this is got a bit more complex setup than the last video, but it's quite clever, especially in the way that it enables us to measure the size of that force. But let me just run you through. Right, we've got the wire, the current carrying wire in the magnetic field is down here, and it's on a top pan balance. I'll give you a close-up of that in a minute, but the full circuit, we've got the power supply, we've got positive red, the current goes through a variable resistor. This is so I can easily change or control the current in the wire. We've got an ammeter to see the size of the current in the wire. This comes up, and then this piece of wire here, I'll show you a little bit of a close-up of that now. So it's just a regular piece of copper wire, but it's quite thick, so it's quite stiff, and I've bent it into that shape so that we've only got a small section here, a short horizontal section of about 3 centimeters long that's actually in the magnetic field. Okay, now the magnets are these two here. I'll show you that in a bit and talk you through that in a second. But that's the section of the wire that's in the field. Okay. Now, let me just talk you through the magnets. Okay, the magnetic field here is these two magnets. Now, these are called Magnador magnets. This is just a piece of steel. We call it a stirrup because it's stirrup shaped. Now, these two magnets here, these are called Magnador magnets. Now, the interesting thing about Magnador magnets is that the poles are on the biggest side. They're on the side of the biggest area. And as you can see, they're stuck together. So that's a north facing a south. Okay, now how do we know which side's north and which side's south? Well, we can use another magnet, a bar magnet. So a north pole is repelling, a south pole is attracting, meaning that that side is a north. Okay? Now, if that side sticks, then that side must be a south. So we can write the south on that. Now, what we do, we put them in here. Okay, so as you can see there, we have a north facing a south. So just like the horseshoe magnet I showed you before, if you have two poles facing each other, it's a uniform magnetic field between the two poles. So the field lines always go from north to south. Okay, so just show you again that they stick together. Right, there you go. So the magnetic field, now this is the really clever bit. The magnetic field, the two Magnador magnets and the stirrup go on top of a top pan balance. Now the top pan balance measures the mass of whatever's on it, okay? But if we set it to 0, now the wire is fixed, it's clamped here, so that can't move. Now, if there's a force on the wire, because the wire can't move, the wire pushes the magnet down and therefore the stirrup down, or pulls it up, depending on which direction. It's a bit of Newton's third law in this as well. If the magnet pulls the wire down, the wire will pull the magnet up. Newton's third law. Anyway, or conversely, if the magnet pushes the wire up, the wire will push the magnet down. Okay? Right, so that's what we can measure here. Now this is the really, really, really clever bit. We've got a value of mass in grams. We can convert that into a force in newtons by using the equation weight equals mass times gravitational field strength. Okay? And that'll give us the corresponding force that's been exerted between the wire and the magnets. Okay? Right, let's see this in action. So let's turn this on. So at the moment I've got the rheostat. It's quite a sizable resistance here. As you can see here, quite a small current. Now the current 0.03 amps is tiny. That's not enough to register a force between the wire and the magnets. But if I take the resistance down, that's going to make the current go up. And if the current goes up, the force between the wire and the magnetic field will start to be significant. And we'll start to see a deflection here. Now what I want to show you here is, we're going back to the F equals BIL equation. Force equals magnetic field strength B times current I times length of the wire in the field. So, first factor, if we increase the current, we increase the force on the wire. Okay. So quite a high current there. 5 amps in that wire at the moment, producing quite a sizable force. But if we take the current down, the force goes back. Okay? Another factor that can affect the size of the force is the angle, is the actual angle between the wire and the field lines. Now at the moment perpendicular, the angle is 90 degrees. The field lines are going from north to south, so the field lines are in that direction. Let's just check our Fleming's left-hand rule again. Conventional current. Conventional current in that direction. First finger field in that direction. That wire is being pushed up by the magnet and stirrup. That wire is pushing the magnet and stirrup down, and that's why we're seeing a positive deflection on the top hand balance. So again, Fleming's left-hand rule is in agreement there, right? But watch this. What if we change the angle between the current carrying wire and the magnetic field? Watch what happens to the size of the force. Okay. At the moment it's 90 degrees. But if I keep rotating, that force, that magnitude of force decreases, doesn't it? And it actually decreases until it's zero, almost. Just gone a little bit too far. Boom. Right, so at the moment, the wire, there's still a current flowing in this wire. There's still a magnetic field, but because the current and the field are parallel, we've got zero force. So that F equals BIL force is 0. Okay? Let's keep rotating. Let's rotate it the other direction. Sorry, let's keep rotating it in the same direction. What do we notice about the deflection now? We've got a negative deflection. This is the north, remember. This is the south. So the field lines have now been switched. So now we've got first finger field in that direction. We've got second finger current is still in that direction, meaning that wire is being pulled down by the magnet and stirrup. If that magnet and stirrup pulls the wire down, the wire pulls the magnet and stirrup up. If it's getting pulled up, that's why we're seeing a negative deflection on the top hand balance. So, there you have it. Quite a neat little setup for accurately measuring the force on a current carrying wire in a magnetic field. Thank you.